So, we just spoke about interpreting our learned classifier. So, we'll talk about learning now, but we spoke about how do we interpret it. And since this was a simple linear classifier, we could interpret the rows of the matrix that we learned in some sense, right? So, each row of our matrix actually looks like an average of our class, and this is what it learns, and you will see it for yourself. But now, let us talk about learning the classifier itself. Now, to be able to learn it, let us first think of a simpler example. Instead of 10 classes, let's just say we have 3 classes and we have only 3 training examples. So, we start with just, let's say, 3 training examples of these 3 classes. What are our classes? Our classes are cat, car and frog. And these are our 3 training examples. Yeah. So, this is our x. So, let's call it maybe x1, x2 and x3, and these are our target classes. Now, x1, so now what we are doing is we are defining some kind of a score, right. So, what we get after our wx, so we get this score. So, when we do this wx and actually wx plus b, but we can ignore b just for discussion, we get this so called score. Yeah. And what we say is this score is in some sense our quantification of our happiness or unhappiness with the output, and we define a so called loss function, and when we speak in terms of loss, it is our unhappiness with the output. Yes. So, we want to have a small number of loss, but a high number for score. And in this case, you see that the correct answers are in the first case the cat, the second case the car, and the third case the frog. But we get a high score for car. So, with this classifier, we would have gotten a wrong answer when we given this example x1. When we given the example x2, we get it correct because we got the highest score, and when we gave it x3, we again got the wrong score and a very bad wrong score because we actually got the minimum, right. If we give x3 as input, we would have gotten car as the output class. So, we defined just now the score. So, this wx plus b happens to be our score. And then we define a so called loss function, and let us say for a classifier we use a so called a cross-entropy loss function. So, the name sounds fancy, but it is actually very simple and we will talk about it. So, remember, cross-entropy is a loss function that you use for a multi-class classification problem. In this case, we have multi-classes because we have those 10 classes, and so we use this Softmax classifier, and we also it is also known as multinomial logistic regression. All these are just complicated words, but when we see, it is actually a very simple function that we define to quantify this loss, and then we talk about optimizing over this loss. So, what we have is our wx plus b, and that gives us this score. And we think of these scores as these unnormalized log probabilities. So, we assume that this wx plus b is giving us probabilities, but they are not probabilities because it can be negative, they do not sum to 1, etc. So, let us change that. So, first let us make it all positive, and let us also make it more peaky. Right? Let us stretch it. And how can we stretch it? We can stretch it with an exponential function. Let us say we use the e to the power x. Right. So, we just take our e and we exponentiate it. We give it e to the power 3.2, e to the power 5.1 and e to the power minus 1.7, and see what it does. So, when we exponentiate all of this, it becomes bigger and bigger. So, 3.2 becomes 24, but 5.1 becomes really big, it becomes 164. So, we have stretched it, and minus 1.7 becomes really small, but all between, so all positive, because now it is e to the power x, it is the exponential function. You could e is just one function we use. You can even use 2 to the power x, 8 to the power x, but on hardware exponential function is probably better defined using lookup tables, and so we use this e to the power x. And then we normalize it. What does it mean, normalize? So I'll just rub this. So normalize simply means that we take this 24.5, right, 24.5, and then we divide it with the sum of 24.5 plus whatever we have, right. So 164.0 plus 0.18 plus this, right. So we divide 24.5 by the sum of all of this, and this is then the normalization, and when you do that you will see that you get 0.13 as the output, right. And this is what we want our highest number to be, right. So we want this to be high, right, because if this is high, if this was, let's say, 0.87, it would mean that I am 0.87 sure that in this case this is the car class, though it is wrong, it should have been the cat class. So how do we learn, how do we kind of go back and change the matrix a little bit, change that W matrix a little bit, and we can do this using this so-called cross-entropy loss. And this cross-entropy loss is actually very simple. All we do is we do the negative log of the correct class. But before we do that, let us also define a so-called targets, right. So we have our outputs. So this output is a vector, in this case of size 3 cross 1. Our targets are also a vector of the same size as output, and in this case it happens to be a one hot vector, meaning we give 1 here and 0 and 0 here. So it is a one hot vector, meaning we give this 1 for the correct class and 0 everywhere else. Okay. So so let us let us write it here. We define our target, and then in this case we define the targets as y. Yeah. So this is our y, and now what we do is we essentially want to kind of say that, okay, whatever is this number, I want it to be as close as to 1.0 as possible, and also note that when we sum it up it becomes equal to 1. So it's a probability distribution at this point, because we have exponentiated it and then we have also divided it by the sum of all the exponents. So now we want it to kind of be 1, and if it is not 1, we are unhappy, right. So we want to reduce our unhappiness. So we define a so-called loss function, and loss function is a function of our output and target, and these can both be vectors. In this case these are 3 cross 1 vectors, but the output is a loss, and this loss is always a scalar, and remember we say scalar essentially belongs to this set of real numbers and real number of dimension 1. If it was a vector, we could have said that the r to the power would be different, but this is again an interview question, and very important to remember that loss is always a scalar function, and the loss function is a function of two vectors, our output and our target. Okay. So now let us better define this loss function. So what we have is our output here, and we say that our output, we will take a negative log of this, yes, a negative log of this, and this will be our loss. Okay. So now let us see what it would look like. Why are we doing this negative log, and what this negative log would look like? So do you know what the log function looks like? If you say plot this e to the log of say e, it will look like this. Yeah. So this is asymptotic to and x, so this is the x axis, and this is our input to the log function, and this is y, which is the output of the log function. And as you know, log of 1, so when the input to log is 1, log of 1 when x is equal to 1 is 0, and as we go negative, right, so as we go closer to 0 in our x in the input of log, we get lesser and lesser values. So as we go closer to 0, the output of log will become closer to minus infinity. Yes. So what we are saying is, if our output was 1.0, log of 1 is 0, so we will get minimum loss. Yes, but if our output is closer to 0, let's say for 0.1, we will be somewhere here, so we will get a very big loss, right? But a negative number, so we have this negative here to make the negative and negative positive, and then we get like a big number, and that big number is essentially our quantification of how unhappy we are with the loss, with our output. So we will then be very unhappy with our loss, with our output, if we get say 0.1 as output here in this case, and if we get 1.0, we will be pretty happy, so we will not be unhappy and we will get 0 loss. Yes, so loss is essentially our quantification of how unhappy we are with the output. If we get 1.0, we are least unhappy, so our loss is equal to 0. If we get close to 0, right, so if we get 1, we get equal to 0. If we output of is 0, then we get infinity as our loss, as our unhappiness. Yes, so this is how we quantify, and when we write it mathematically, we have to, it looks complicated, but it is not, because see, what is y? Y is that one hot vector, it is our target vector. In this case, it happens to 0, 1, 0, 0. And then what we are saying is, we want to then, so Li is each of these, right? So Li is negative log of this into this, and then so that is Li for I equal to 1, then L2 is negative log of this into this, and then negative log of this into this. So this is L1, L2, L3, and our final loss is nothing but, so our final loss is nothing but the sum of all Li's. In this case, it is just L1 plus L2 plus L3. And if you see, there is only one term which actually the one term which is actually non-zero, right? That is actually responsible for creating the loss. Everything else will be 0, because in our one hot vector, everything else is 0, because we multiply it with 0. So cross entropy, remember just one thing, it is just the negative log of the correct class. Okay, so what is cross entropy? Cross entropy is nothing but the negative log of the correct class, the negative log of the output of the correct class. So if we look at it, we don't care about what is the output of these two classes, we just care about our output here. They could, so our output here should be high. If it is not high, we will see how unhappy we are with that. How do we know our unhappiness? By doing the negative log. Why the negative log? Because log will basically make it more peaky, right? And log will look at, let's say, log of 1 is 0. So if our output is high, if our output is 1, and it cannot be more than 1 because we have normalized it. So if our output is 1, we are not unhappy. If our output is 0, we are super unhappy, and our loss is, infinity. So this is how loss functions work. Loss function, the input are two vectors, output and target. The output of loss is just one scalar value, just a single number in this case.